It's a wonderful moment to start. Let's welcome everyone. Thanks for coming. And it's my great pleasure to announce our virtual guest today, Gregory White, who's speaking from down under today, like from the other side of the planet, pretty much. I think Sydney is
pretty much
on the other side of London, so Melbourne, yeah, it's not quite on the other side, but it's pretty much as far as And he's coming from the University of Melbourne, but also from the IBM Quantum Network Hub at the University of Melbourne. And he will bring together a couple of topics that we are also much concerned with when he's speaking about capturing the many-time physics of quantum stochastic processes. So thanks for electronically coming. That's great. And yeah, thanks for giving the talk. And the stage is all yours.
Awesome. Well, thanks so much for having me. And yeah, thanks for tuning in, everyone. So yeah, as Jens said, today I'm coming from the University of Melbourne, and I want to talk a little bit about how you capture the processes, capture the many-time physics, I should say, of quantum stochastic processes. So in particular, so I just want to please, just to give a rough outline of what the talk's going to look like. I want to give it a bit of background on how you generalize some concepts in classical probability theory, and how to kind of think intuitively about quantum operations and the sort of correlations that crop up in that respect, with the guiding aim that we want to get to thinking about non-Markovian quantum processes and really understand why it's difficult to generalize this from the classical case into the quantum case. And then we'll introduce a framework known as a process tensor framework, which describes or formally generalizes the classical stochastic processes to the quantum setting. And really, they really formalize this idea of what multi-time quantum correlations look like. And then I'll delve into some results in characterizing, controlling, and diagnosing non-Markovian processes. So broadly speaking, this talk will cover these few references here, so bits and pieces from those, and I'll kind of flash up the references as it becomes relevant if you happen to want to check out those references. Feel free to jump in at any point if you have any questions. I think makes a lot more sense. And if it does turn into a discussion and we don't get through all the slides, then that's totally fine.
Good.
So I assume, is it?
Wonderful. That's great. Very good.
I've aimed for about an hour, but yeah, we'll see how we go. Cool. So I think a good place to start is to kind of really give a sense of what we think about when we say many-body physics. And I would say this is sort of like the quintessentially interesting thing about quantum physics, which is that you have some quantum state and that's, breaks up into lots of little subsystems. And ideally, if the state is going to have some structure, then those systems are correlated with one another in that they contain kind of more information if you look at them together than when you look at them separately. And in particular, you access these correlations by making measurements in different bases and building up different probability distributions. So we can go from totally boring classical distributions with only sort of really access by one measurement type, all the way to nice quantum interesting distributions from which you can glean many different measurement types. And the sort of physics here is a lot more interesting and can be structured. There's a lot of interesting physics in how correlations are distributed across subsystems of a larger quantum state. But what we're interested in today is not so much many-body physics, but rather what we call many-time physics, which is that we're not asking about a single state at a single time, but we want to consider the scenario where you have a single accessible system, so something that you can control, and think about how that evolves while it's coupled to some inaccessible environment. And the rough picture of how these correlations can crop up is that these system environment interactions, they can mediate an exchange of information. So information passes from a system into the environment and then comes back at a later point in time, generating these interesting joint statistics. And in particular, these can be totally quantum. And so what we're interested in kind of asking a question of is, what sorts of interactions kind of generate these temporal correlations and how can they be structured? So how can they look the same way as spatial correlations? And in particular, how can we kind of access, measure, and manipulate these temporal correlations? So I'm not going to focus so much on the first two, although a little bit of background, but I want to talk about the third one. And this kind of topic is really key for the study of open quantum systems, which is the heart of, I would say, all quantum physics. Like any physical system that you care about enough to fabricate or to study is generally going to couple to some inaccessible external environment, maybe with the exception of photonics. And so you can consider this in the context of maybe correlated noise in quantum computers, but also in a condensed matter system, in a quantum biological setting, with respect to quantum chaos, complexity theory, sensing, the list goes on. So there's a lot of motivation to kind of study this interesting problem.
Maybe a question before you continue. So you're both interested in the discrete time and the continuous time setting, right? Like more physicsally motivated by actual processes interacting with actual environments on the one hand, and having quantum circuits where you have got an obvious temporal order by applying quantum gates. Is that right? And either way, you are interested in like memory effects, so that there's some bath coming in and there's kind of potentially complicated and complex ways in which the kind of distinguished system, the accessible system, would interact with the bath and how the information might come back in one way or the other. Is that right?
Yeah, exactly. I would say we think less about the continuous time viewpoint because it's more of like an operational approach. And so I think the discretization and maybe the circuit structure is maybe more in line with the way that we sort of think about these things. But everything that I discussed is consistent with a continuous time
Wonderful
modeling.
Okay. Thank you very much.
Cool. So before we jump into that, I just want to consider some quantum analogs of classical probability theory, just to provide a bit of background. And the reason why we're interested in probabilistic concepts is because if you're coupled to an environment and you don't have access to all those environmental degrees of freedom, then on like a shot-by-shot basis, you're sampling from some ensemble. And so what's left in the dynamics is no longer nice deterministic Schrodinger evolution, but rather it's this kind of probabilistic setting. You know, so in the kind of the prototypical sense, you would describe the state of a classical probabilistic system by some probability vector, which generalizes in a quantum case to a density matrix whose eigenbasis, as we know, is a convex mixture of pure states. If you're thinking about one time to the next, then probabilistically, you might use a stochastic matrix mapping a probability vector from one time to the next. In the quantum setting, you can think about this in terms of quantum channels, which are mappings of density matrices that take you from one time to another. But what we're going to be interested in looking in is multi-time non-deterministic processes. So in a classical setting, these are stochastic processes, and these are just broadly described by a series of joint probability distributions. So you have the joint statistics of different events occurring at different times. And we want to ask the question, what does this look like in the quantum setting, so that we can think about joint statistics in a fully general way. So to kind of build up this idea that times can be correlated, it's good to start from the two-time setting, which is the quantum channel setting. So in this sense, we're interested in asking the question, how can an output state, or how is an output state correlated with an input state subject to some quantum channel? And this is formalized really by a famous relationship known as the Choi-Jamekovsky isomorphism. So just briefly, if you're not familiar with this, essentially what this says is that the set of maps that act on a quantum state is isomorphic to some subset of states that are on this bipartite Hilbert space, so the tensor product of your input-output Hilbert space. And so kind of canonically, the way that this is realized is that if you take a maximally entangled state and you put one half of it through whatever your quantum map is, then you can show that element by element, the state that you get at the end is identical to the quantum channel, or identical to the map. And so you can identify the properties of this state with properties of the channel. And that makes it a lot easier to kind of think about, because typically we're all really familiar with states. So to kind of make this concrete with some examples, here are some, I guess, just two-time control maps. So ways that you can manipulate your quantum state and their corresponding choice states. So just like a unitary transformation, a deterministic transformation of a state has a maximally entangled choice state. And you can read this as being the statement that a unitary channel preserves all quantum information. So everything that you go in, every bit of information that you put into this channel can be reversibly kind of backed out. But at the other end of the spectrum, you can have something like a measure and prepare channel, which is that you measure your incoming state in some basis, record the output, throw away that state, and then re-prepare a brand new state. And this choice state is it's a complete product state, because whatever comes out of that is totally independent of what went into it. And you can do crazy things like completely depolarize or throw away your state. So you might scramble it and re-prepare a maximally mixed state. And so this choice state is not only a product state, but it's completely, it's a complete uniform mixture. And you can get in things that are in general in between these. So you can get properties like separability, partial entanglement, and anything that kind of lies in between with respect to these is how you can kind of think about these quantum maps. And just to, while we're on this note, I just want to introduce a bit of terminology in case it's not familiar to people, which is that of a quantum instrument. So a quantum instrument is essentially just this non-deterministic quantum mapping. So it generalizes the notion of a POVM where you obtain some classical output, but you also have like a post-measurement state. So in this case above, this is a quantum instrument where you make a measurement, you don't get to choose whether it's a 0 or a 1, and then you re-prepare something. So there's a post-measurement kind of state. So this is like, I would say, how you think sort of formally about the idea of what two-time correlations look like in a quantum setting. But it's not particularly interesting because by default, the identity channel is maximally entangled, right? Like the most boring thing you can think of has kind of this maximal amount of correlation and transmits all this quantum information. So we want to go forward through to more times and to kind of consider how these can be set up. And to do so, we need to look into stochastic processes. So to return to the definition from before, if you're considering classically some non-deterministic process, then everything you can learn about that process is described in the above series of joint probability distributions, which essentially just says this is the probability of my system being in state xk at time tk, as well as xk minus 1 at time tk minus 1, all the way up to x0 at times t0. And this tells you everything that you'd like to know about the dynamics, but it's an exponentially complex object because you need to consider all combinations of all elements at all different times. And so some particularly nice, some dynamics which satisfy a particularly nice structure are these of those of Markovian processes or memoryless processes. And these say that the future statistics of the system don't depend on the whole history of that system. They only depend on the state at the previous time step. And so now what is an exponentially complex object is reduced to just being linearly difficult to describe. And you can do things like derive master equations and reduce to sort of nice continuous time.
So that's basically the kind of constraint. I mean, in mathematical terms, that's kind of a constraint to the Chapman-Kolmogorov forward equation, right? To be factoring.
Yeah, exactly. Cool. So, I mean, I guess like two straightforward examples of stochastic processes at alternate ends of the spectrum. You might roll some dice again and again and again and obtain outcomes, and you can just predict the outcomes by saying the dice have a 1 in 6 chance of landing on each surface, on each number at each different time. But at the other end of the spectrum, you can have a really difficult process, which is that of the share market, which people try really hard to try to understand, whereby you might predict, you might assign a whole bunch of different probabilities to future trajectories based on past data. And there are a lot of reasons why this right process has a lot more structure than the left one. But principally, or part of what this includes is the ability to have past future correlations. So things can happen in the past, which might drastically influence the share price in the future. And so if you were to know all this information, you would still have a difficult time in terms of actually modeling what's going on. So why am I telling you all this? Why are we interested in this? Well, I guess it's to go back to before, any system that you're interested in quantum mechanics is invariably going to couple to an environment. And as soon as you trace over the degrees of freedom of that environment, it means that the corresponding dynamics at the system level is no longer deterministic, it's probabilistic. And so this gives rise to familiar stochastic errors that you might be familiar with, like relaxation and dephasing, but also more exotic effects where there's some kind of a memory involved, and these are called non-Markovian stochastic processes. So to give kind of just like a rough feel for the difference between the two settings, in Markovian dynamics, you maybe have a weak coupling to your environment, and the environment is relatively large and dissipative. And so information only really travels in one direction. And so to describe these dynamics, you only need to track the state of the system as well as what information is leaking out, which is not ideal, but it's relatively straightforward to do. And you can do that with the aid of master equations or just the quantum channels that I flashed up before. But in the non-Markovian setting, where you maybe have a stronger coupling to the environment and maybe a smaller, more coherent environment, you can have a mutual exchange of information. And this becomes problematic because what might happen is that you might apply a gate to your system that determines what information goes to the environment. The environment sort of sits and digests that, and then passes information back into the system at a later point in time that now affects the system in such a way that depends on whatever operation you applied at the earlier time. And so this makes it a much more complex scenario to describe. And in fact, it's been an open problem for a fairly long time, how to kind of come up with good non-Markovian, good descriptions of non-Markovian quantum processes. Great. So in thinking about quantum processes, we've done all this generalization. You might wonder whether you can take a classical Markov condition and apply it to the quantum setting. And there's a variety of technical reasons why you can't do this. But principally, implicit in this equation is the ability to actually observe your system without affecting its future evolution. So in the classical setting, when I'm rolling dice, the fact that I see that I rolled a 6 doesn't affect anything about the future evolution. But in quantum mechanics, as soon as I make a Z measurement or an X measurement, then it collapses the system. And so my measurement, my active measuring, is actually invasive now. And so all bets are off. And so the issue is that my choice of measurement type affects the future evolution of the system. And so now, even if I adopt this kind of open quantum systems picture where I'm tracking the state of my system as a function of time, I can't fully measure correlations which are non-local in time. You can only do things from this point of view which infer non-Markovianity. They don't come up with necessary and sufficient definitions of Markovianity. So an alternative approach that you can take is to adopt that of quantum stochastic processes, which sort of says that in real life, in the lab, an experimenter doesn't actually have access to a quantum state. They have access to a series of control knobs which manipulate that state. And so every time you apply an operation, every time you manipulate your state, you're affecting its trajectory in some way. You're pushing it off path. And you can measure the response of your system at some final time, conditioned on whatever operation you applied. And since quantum mechanics is nice and linear, if you apply 2 different operations that send it in 2 different trajectories, the general idea is that you can infer things about intermediate trajectories just by taking linear combinations of those 2. And so the kind of idea that we want to build up is that there's only like a finite size super operator space of things you can do to a quantum system. And so if you do enough different operations to fill out a basis of that space, then that describes everything that you might like to know. So kind of the picture that we're dealing with here is that you have some accessible system. It's coupled to an inaccessible environment via a series of arbitrarily strong unitaries. And we're driving it. We're just driving it with a sequence of control operations, which might be unitaries, they might be measurements, they might be anything in between. And what's described or what's depicted in blue here is an object known as a process tensor. So the kind of opaque definition of a process tensor is that it's a multilinear mapping which takes in sequences of operations at different times and outputs a state conditioned on those operations. But kind of intuitively,
to be sure, sorry, because the blue is not particularly clear, but that's also maybe my color perception.
Sorry, yeah, no,
Everything
it's
that's not
light
yellow and not green is the blue stuff, right? That's
it's
some
it's the comb-like part of this.
wonderful. Yeah, I anticipated that. Thank you.
So the process tensor, it represents everything which is uncontrollable here. We're really, the emphasis is that we're partitioning the things that you are in charge of. So you input a control operation, and the system and the environment take care of the rest in terms of their dynamics. And so this approach to things, it doesn't average over any part of the environment. And so that means it's valid for arbitrary non-Markovian processes. And in fact, as we'll see in a moment, it constitutes a necessary and sufficient definition of Markovianity. So I just want to quickly unpack this idea of what a process tensor is doing and really kind of scrutinize it. So every time, so if we have some window of dynamics, then we're probing the system at some number of times. And you can imagine that at each of these times, as you apply an operation, the state is coming out of the process, it's going into, however, your control instrument, and then you're feeding it back into the process. And you're kind of repeating this as you drive it along a series of dynamics. So if we zoom in on just one of these steps, then this is a quantum channel exactly like before. And so I put in a state, and what comes out is correlated in some way with what goes in. But if I zoom out a little bit and look at a couple of times, then what I might see is that by virtue of this system environment unitary, this might change something about the environment. It might unlock some degrees of freedom. It might switch some, drive some transitions, and then the environment will carry that forward as a memory and come back to the system at a later point. And so now when I feed a state in, what comes out is not just dependent on whatever went in, it also depends on what I did at this point at T0. So it also depends on the operation that I applied just here. And so this is sort of like the quintessentially non-Markovian behavior that we're talking about before, which is that my choice of past operation or something I did in the past, or maybe an outcome that I observed, is in some way affecting the future statistics or the future evolution of the system.
Sorry, can I ask a question?
Yeah.
Hi. So do the operations A1 and A0 and so on, do they need to be like independent, or can I also consider something like, some memory effect or some feedback also on there?
Yeah, that's a good question. So they don't have to be independent of each other. I've kind of shown them as being independent just to kind of ease into the idea. But you could consider, say, for example, this yellow. If this were an ancilla qubit and I drove, say, a 2-qubit operation and I interacted my system with an ancilla at each time, then this would constitute a correlated operation. Or maybe like, maybe you insert some classical randomness where you apply a laser pulse and you draw like a random number generator, and then you add on some coherent, something coherent to the gate, and you do that every gate. That would institute some classical correlation between them. So it's a fully general kind of model in that sense as well.
Okay, thanks.
Cool. So the thing, I guess, that's important to take away from this is that this process tensor, this kind of viewpoint is that you're driving a system along, and the process tensor, or the fact that the control exists outside the process tensor, means that you account for the effects of these control operations. So you can separate out what's something that in my environment did to me and what is a consequence of my instrument. So what is a consequence of my choice? So in a sense, what's happening is that every time you run a sequence of operations, you're learning a little bit about this stochastic process. So if you kind of zoom out a little bit, it's important to kind of emphasize that the process exists independent of our control. You as the experimenter get to choose to probe the process, but it exists outside the realm of your choice of control operations. And so, suppose you were to choose a sequence of instruments. So I chose a sequence of, say, weak measurements, which did something to my system. I got some outcomes, some series of measurement outcomes at the different times. And what this would look like is this would look like a joint probability distribution that tells me about all my outcomes xj at time tj. For the these are joint statistics at different times. and they're conditioned on whatever series of instruments you decided to apply. So you can think of this in an identical way to if you have a quantum state, you pick a basis in which you measure that state, and then you get a series of joint probability distributions which describe those measurement statistics conditioned on some basis. And so what this object does is it actually formally generalizes the notion of a classical stochastic process to the quantum setting.
But not only that, I mean, I see the interpretation, everything is crystal clear and so on. But I mean, as an abstract object, it's also really not only a process tensor, but it literally is a tensor, and it can be seen even as if you construct parts of it. I mean, it's really a literal matrix product state, if you want, with the temporal guys taking part of the physical degrees of freedom and so on. I mean, that's really literally a matrix product state, correct?
Yeah, precisely. Yeah, exactly right. So each of these points, these are legs of a tensor. And so these can be thought in a sense like qubits, where, you know, at different times you might make measurements, and at other times you might say project input legs on different states that go in. And so actually this idea is formalized by a generalization of the earlier Choi-Jamekovsky isomorphism, which says that if you input 1/2 of a maximally entangled state at each time and then kind of reshuffle those at the end, then the state, this 2k plus 1 partite quantum state, is element by element identical to the quantum stochastic process. And so any possible temporal correlations are exactly mapped onto spatial correlations between the different subsystems. And so you have, if we look at specific legs, we can see that the, this first leg that comes out, that's the average initial state. If we look at the next couple, this marginal here is the marginal quantum channel of the next one, but they're all possibly correlated. So it allows for the possibility that, say, at a measurement at this point or an operation at this point, updates, by virtue of me having made that measurement, it updates the future quantum channels, so the future marginals of the quantum channels.
Sorry. Can you explain this again? Sorry, I mean, this is very fascinating. Can you be a bit slower on this? Like, I want to understand this generalized Choi-Jamekovsky isomorphism. I've never heard of it.
Yeah. Okay. So did you want me to re-go?
Yeah. Just if you can repeat what you just said, maybe.
So in the canonical Choi-Jamekovsky isomorphism, you have a quantum map and you act it on 1/2 of a maximally entangled state.
Yeah.
And what this kind of looks like is it looks like you're doing tomography sort of in quantum parallel, because 1/2 of a quantum state kind of, it locally has full Schmidt rank. And so you're sort of applying that quantum channel to a full basis of states all simultaneously. And so you can extract all the information about the channel from the bipartite state. You don't actually have to experimentally realize this or anything. This is just kind of the mathematical formalism behind it. Now, if we take this to, I guess, its extreme, is that if we want to consider a k-step process, then at each time we swap in 1/2 of a maximally entangled state. And so now, say this unitary here, this is acting on 1/2 of this initial bell pair. This is exactly like a unitary which acts on this leg is exactly the same as the output leg which comes from this stochastic process. So you can think of it like you are, what's the best way to put this? You can think of it like if I supply 1/2 of a bell pair at each point in time, now I'm acting my different unitaries at different times. Those are acting simultaneously on a complete basis of joint inputs to the process. So it's sort of like saying that I can determine what happens when I have my unitary acting on a 0 state, a plus state, a minus state, and a 1 state or so on, at the same time as it acting on a 0 state, a 1 state, a minus state, and so on at maybe a later point in time. And so what that allows you to do is it allows you to know exactly, kind of how do these things jointly affect the dynamics. So it's a little
Okay,
bit,
no, I see. So basically, I mean, also the number of these, I mean, depends on how many kind of like instant of time you perform, right, this operation on. Like, I mean, I mean, and so, I mean, how does this kind of like relate with the continuous measurement picture that Jens was mentioning at the beginning, right? I mean, if you imagine to kind of like continuously measuring the system, so that basically you're kind of like doing this infinitely fast. Can you do this Choi-Jamil-Minkowski also in this kind of like infinite dimensional case, in a sense?
Yeah, so that's actually it's a really good question, a really large part of how this satisfies these Kolmogorov extension theorem conditions. Okay. So the important thing, I guess, is that, so firstly, you define the process. So you choose a series of times at which you want to probe the system. And so you have, your defining setup is time 0 and time, final. And then you pick, I'm going to look at K steps. And these are the correlations which we're going to investigate. But the underlying process exists. And what you can imagine is that you might discretize the process into infinitely many steps. And in the process of coarse graining into, say, 3 steps, what you're doing is you're saying at each of these other steps, at each of these other times, I'm applying the identity operation. I'm just letting the system evolve by some delta t. And so in that setting, you can mathematically completely describe a continuous time process in this way. There might be some subtleties when you go to continuous, like infinite dimensions, but you can describe these continuous time processes in these way and think about when you're coarse graining that process, what you're really doing is you're saying for certain windows of time, I'm just letting my system evolve. Right.
No, that's why I was mentioning not like continuous process, but like continuously measured process.
Yeah, so in this kind of picture, you could consider maybe like a continuous measurement, so some finite time measurement where you're integrating over a signal or something like that.
I see.
You've got something a little bit happening to the system at each of those times, and you would then integrate over that whole effect in order to say account for a continuous time or a finite time measurement.
Thanks a lot.
Cool, no worries, good questions. Great, so just to kind of distill this.
If I'm having another break, can you go back to the slide? You said that the stuff you do, like the A's, are essentially observables of the process. If you go to this other generalized Choi-Jamil-Minkowski isomorphism picture. I mean, can you maybe say something intuitive about, like, since you also, Giacomo said, if these controller operations are independent, or if you just like also on the control side have like a CUMP that you put in, how do the observables that you get for those look different?
Sorry, I missed that last sentence, if you wouldn't mind repeating.
Yeah, sorry. So the thing is that Giacomo also asked if you can choose these operations, these A's that you put in independently, or also with the memory system. So you kind of push a CUMP also from the below side. And you said that like these control operations, they constitute observables in this Choi-Jamil-Minkowski picture. And I mean, how are those observables different if they are like have a memory system or not?
Well, this is actually a good question. And in some sense, they're not different. So the control operations or the possible, these memory, like a comb from below, this is just the joule to what a process tensor is. So they're not different. They're different, I would say, in a couple of ways. They're not ontologically different, I would say, in that they're sort of the same object, but they are sort of epistemically different in that we are choosing the control operation. So there is some amount of experimenter control which we're afforded. And so if we assume that we know the control operations, then we can distinguish what effects come from the process and what effects come from the control. The other way that they're different in a mathematical sense or in a physical sense is that a process has to satisfy some causality. So it has to be, broadly speaking, trace preserving, like at the end, I should get a unit trace process because I've averaged over all these environmental degrees of freedom. But the comb from below, or its formal name is a tester, if you want to look these things up. A tester doesn't have to satisfy the same thing, because you could have it be a non-deterministic instrument. So if you make a measurement at the end, then that's not a trace preserving operation, because you'll generically be projecting your state down to something which reduces its trace. But to answer your initial question, physically the two things are more or less identical.
Cool. Yeah, thanks.
Does anyone else have any questions at this point?
I'm happy.
Okay. So just to kind of distill this all down, this is what we mean when we use the term many-time physics, which is to say that quantum stochastic processes, these are systems that interact with their environment, and by virtue of that interaction, they can have temporal correlations. And so with every multi-time process, we can identify a quantum state, and we can identify the temporal correlations with these spatial ones. And so if we want to think about, how do we study temporal correlations, then this is the framework to do it, because we can use our usual understanding of multipartite quantum correlations in a quantum state to understand these processes with some extra structure. And so just to reiterate before, the series of control operations that drives the process, these constitute these observables on a many-body state. And so what I want to talk about now is how to actually study these correlations and how to kind of extract information out of real multi-time processes. So to kind of do so, we're looking for an object which works exactly as I kind of discussed before. So we're looking for a multilinear mapping given some experimental setup, which takes in an arbitrary sequence and outputs a state which is conditioned on those operations. And so one thing you can observe is that as a linear operator, it's fully described by its input-output relations on a complete basis. And so one way to find a basis for my arbitrary sequence is that I can expand each time local operation in terms of a series of basis elements for that particular time. And so if you want to reconstruct the whole process, it suffices to measure the final state conditioned on all basis elements in position 1, as well as all basis elements in position 2, all the way up to all basis elements in position k. And you can see that by virtue of this linear expansion, everything about the intermediate dynamics is totally preserved. So nothing is averaged over, and so the unitaries can be arbitrarily strong. And if we trace over all this input information, we're left with an expression for this final arbitrary state in terms of some known expansion coefficients and some measured basis states. So this allows you to kind of reconstruct, in a broad sense, these non-Markovian processes. And we tried this out on some IBM quantum superconducting devices. And this particular relationship it gives rise to like a natural figure of merit for the characterization, how well the characterization went, because you can come up with some prediction for an arbitrary sequence, and then you can go away to the actual quantum computer and actually run that sequence and compare how close your prediction was to the actual experimentally observed state. And so here what we have is a series of experiments in different dynamical setups on these devices, and each data point constitutes a randomly selected sequence of unitaries. And on the y-axis here, we have the fidelity between the predicted state with the experimentally reconstructed state. So in this setting, we can see that this orange number tells you the median reconstruction fidelity for each thing, which is about 0.999 for each one, or well within shot noise. We can also look at how it performs do like a 0-1 kind of testing sort of thing, and look at how it does in a non-Markovian setting versus a state-of-the-art Markov model technique in gate set tomography. So GST is, if you're not familiar with it, it's state-of-the-art for benchmarking quantum gates, and relies on the assumption that the dynamics can be sliced up into independent series of maps. Now, the other bit of detail which is relevant is that these transmon devices, they have like an always-on ZZ coupling between each qubit and its neighbor. And so you can kind of flick the switch and you can put that neighbor into a plus state, and that will allow you to couple to that in a non-Markovian way. So we looked at neighboring qubit in a 0 state and neighboring qubit in a plus state. And in both scenarios with the process tensor reconstruction, you get quite a good recovery. Whereas in GST, it does quite well with the neighboring qubit in a 0 state, but when it's flicked to a plus state, the model breaks down and it's no longer sufficient to describe the dynamics. And so this sort of demonstrates that there's like a complementarity to these settings where you can reconstruct non-Markovian dynamics in a situation where Markov models break down.
Can I ask a question? Sorry, that's a bit nitty-gritty, but I mean, to relate this to randomized benchmarking, I mean, randomized benchmarking does make this Markovian assumption. That's probably the one that's really most difficult to get away with, to get rid of, sorry. Well, there's ways, but other than that, it works in like remarkable generality. That works for like many different groups and lots of different settings. And the upshot is, if your implementation map, like your real implementation of the physical system, is like close enough to the anticipated one, to the ideal one, in a precise sense, like in a diamond norm sense, then one really finds that the signal you get at the end of the day can be seen as a sum of exponentially decaying terms with an error bound that can be really fully bounded and quantified. So in this sense, the RB problem can be really nicely related, and you also can see how the classical post-processing works, in that you can really relate this to the average gate fidelity and so on. So what's the deal here? So here it's right that the process is multilinear. So once you fix the basis, that's fully characterized. But if you do this, like what type of characterization do you hope to get? You talk about the reconstruction fidelity, but can you add more detail concerning what the reconstruction fidelity precisely is, and what like recovery guarantee you hope to get at the end of the day? Or is that maybe a strange question? You can also delegate this to later, but I'm just asking for a bit more fine print what it means to characterize these process tensors.
Yeah, it's a good question. So we'll probably cover in a bit more detail in slides, but to give kind of like a short answer, I would say that in any characterization technique, you're sort of interested in both extrinsic behavior and intrinsic behavior. So you have a model, and the extrinsic behavior is it able to predict aspects or features of the dynamics which come from outside the model. And so in this case, this is a purely extrinsic viewpoint, which is looking at saying, can we reconstruct in a meaningful way? Can we make predictions for what the dynamics looks like subject to some different series of gates? The other kind of aspect, I guess, the intrinsic one is that we'll get to is looking at the actual structure of this choice state. So looking at the actual, kind of quantitatively saying, this bit is entangled with this bit, and saying something about the dynamics in this sense. What I think an extrinsic, what this reconstruction fidelity is really useful for, is that if you have like a nice mapping which says exactly what state you're going to get at the end, then classically you can do all this optimization to say, well, I want to find the sequence of gates which gets me some desirable property of my quantum state at the end. So if you can say that I know exactly what sequence of gates gets me this state, then you can do it all numerically. You can do the characterization once and then numerically look for how to kind of optimally control your device, even in a non-Markovian setting. Does that answer your question? Sorry, I might have gone off on a tangent.
I was muted. Sorry, that totally answers my question. Thank you.
Okay, great.
Can I also?
Sorry for the many questions, but I did warn you. Sorry.
No. This is great. My one concern is I have many slides to go, and we've only got 12 minutes left on the hour. Is that a problem, or should?
Yeah, no. Then I will ask it later. Maybe you will.
No. So please ask it
in the next slides.
No, if I don't finish my slides, it's fine. I'm more wondering if you all have places to be.
No, I will postpone it at the end.
Let's do both. I mean, let's continue. I mean, we're not strict with time, but we can still have the question at the end, because we asked so many questions, which is great. I mean, you asked for it, but never ask for this. This can mean that there's lots of questions. But anyway,
no, No, it's great. I really am enjoying the discussion. Cool. So I guess with all that in mind, we're now in a position to sort of formally introduce process tensor tomography, which is that we want to be able to reconstruct this choice state representation of a process given some set of experimental data. So as I kind of alluded to before, this generalized Born rule is what connects your process tensor to like a realistic model. So you project your process tensor, the choice state of that, onto a series of operations, and that will give you a probability distribution. And you can then compare that probability distribution to the experimentally observed one and update the estimate accordingly. So using this idea, we developed a maximum likelihood method, which finds the process tensor, which is as consistent as possible with the experimental data in a way which it's also physical. So it needs to be positive. It should produce positive probabilities. And it also needs to be causal in that a choice of future operation shouldn't affect any past statistics. So we developed some algorithms to kind of, with some guarantees to find this process tensor estimate for any set of dynamics. And so the result is that it gives you a purely operational estimate of this non-Markovian quantum stochastic process. So in a way which doesn't depend on any of the physics, it's just a series of input-output relations on some complete set of basis operations. And so this can be a way to understand generic open quantum dynamics, and as we'll see in a particular case with noise reduction in quantum devices.
Gregory, do you also have theoretic guarantees on this, or is this just like a protocol that you developed? Because it looks like it's probably hard to prove stuff about this, right?
In this particular case, this, I mean, the maximum likelihood estimate of this form is a convex optimization problem, and we solve it through some projective gradient descent, so that by virtue of using this approach, it comes with guarantees of convergence.
Nice.
Not, yeah, in terms of the optimality, I have fewer things to say because I think it's a harder and sort of a problem that I haven't really considered as much, but it is guaranteed to give you the maximum likelihood estimate up to some epsilon.
Yeah, I mean, I can endorse that. I mean, this is an interesting question. I think one should look at guarantees here. I mean, many of the ideas on shadows, and I mean, that's very much of a Johannes topic, right? I mean, many of the shadow ideas and the channel shadow ideas and the randomized benchmark ideas that would presumably might, like, to a large extent carry over, but this is hard work. I can see that.
Yes, yeah. So I mean, this is, I would say, a probably much easier version of those problems. One thing I do want to point out, actually, with respect to that, now that you say that, is that so as I said before, these operations, they can be whatever. They can be unitaries, they can be measurements, and anything in between. But you're very much constrained by what's available on your device. So not all devices, for example, have mid-circuit measurement capabilities. And if they do, they tend to be quite noisy and quite long and invasive. And so in this particular instances, we say, for example, we're restricted to series of unitary operations. But unitary operations are not informationally complete. And so you end up learning something about the state propagation, so the propagation of the state, in order to predict how that kind of propagates along. But you need mid-circuit measurements in order to give you the marginal statistics, or you need some kind of a quantum instrument to give you the marginal statistics. So if you do this in an incomplete setting, like a tomographically incomplete setting, then you end up with a non-unique estimate of the choice state, which is only valid across, or only consistent across this unitary subspace, that span of unitary controls. Great. So with that in mind, I guess, like, the first thing that you might be interested in looking at is, can you detect temporal entanglement structures? And in particular, just building off that last point, we want to ask the question, can we, if we constrain our observables, so we're looking for entanglement witnesses that act as an entanglement monotone, and we want to add this extra structure that if we constrain the witness to be in the span of unitaries, can we still measure temporal entanglement? And as it turns out, the answer is yes, which was quite surprising to us, because essentially what you're doing is you're sort of saying, you're looking for bipartite or genuine multipartite entanglement in time across these different structures, but you're applying deterministic operations at these two different points, and the kind of the measurement aspect only occurs at the very end in the terminating case. So what we have here are a couple of different experiments where we interact the system with its ancilla neighbor through this interaction here, and basically vary the strength of that interaction, and look at how characterize the two-step process in this first scenario, and then look at how these constrained witnesses, or how these constrained kind of measures able to detect the level of temporal entanglement in each scenario. So we see that the GME kind of maximizes at about πm4 of this interaction, and then the bipartite maximizes at the very end. And a way to understand this is actually that when theta is equal to π/2 in this instance, the two gates multiply out to be a swap gate. And so the gates are each a swap gate. And so you can think like your state is being swapped into its ancilla, and then it's being swapped back into the system. And so only the start and the end of the process are kind of are meaningful. So you could transmit quantum information. It would take this sort of roundabout way to get from the start to the finish, if that makes sense. In this second instance, we're looking at the effects of not so much the effects of varying interaction, but rather if you fix the interaction between a system and its neighbor, how much can local control affect the amount that the quantum structure changes. So here we have a three-step process, which we characterized, and then we projected the first operation, so this being the 0th operation and then this being the first. We projected that onto some parameterized unitary, and then looked at the entanglement between each half of the process as a function of changing that unitary. And so as it goes from identity to Y to Z to X, the entanglement, the bipartite entanglement can vary quite substantially. So this sort of shows how local control of a process actually gives you, it actually means you can turn that process into something which is either more or less complex based on whatever conditional choice you made. Great. So if this is all sounding very exponentially costly, well, that's because it is. And as I alluded to at the start, that's true even for classical stochastic processes. So these are, if you account for a whole history of a system, then that's a tree which kind of bifurcates with every step. And so ends up being an exponentially difficult object. But you might, rather than having a totally non-Markovian process where the whole history is relevant, you might instead only have a system where the previous finite number of operations update the future statistics. So if I can average over everything but the previous L time steps and I still get the same future statistics, then I don't actually need to track that whole history. I can keep in my memory just this finite kind of memory block. And for technical reasons, this doesn't generically extend to the quantum case. But we can motivate, or we have this idea where the past and the future can be approximately independent of one another, conditioned on some set of operations acting on a finite memory block. So kind of taking this idea and running with it, we have developed this method of applying this conditional Markov order ansatz to quantum stochastic process settings. So here we have a 4-step process, for example, modeled by a sequence of 2-step overlapping process tensors. So what's kind of happening here is that the first process tensor, you contract in the first 2 operations, and that will update the state conditioned on those 2 operations, and then feed into the next process, and the next process will then be aware of operations 1 and 2, and then feed into the final process. And so at any point, we only need to keep track of the L-step marginal process tensor, which means that the characterization is now linear in the number of time steps.
Sorry, I have a question here. Does this letter, like I don't know what's the name of it, like this kind of
The epsilon.
Okay, yeah, the epsilon one. So is it just the same for the sake of like clearness, or do they have to be the same tensor process tensor here? Because I mean, if I remember correctly, I mean, this is also determined by the initial state, right?
So yes. So just for clarity, so these are not the same. Well, do you mean the 2, 0 and the 3, 1? Are these the same, or?
Yeah. So I mean, if the epsilon 2, 0 is an object which is, I mean, is different from the epsilon 3, 1, or if it's the same thing but just with the time argument different, you know?
Oh, so it's a they should coincide on places where they overlap. So these are different objects in that the dynamics can update. So I could have like a different set of dynamics at a later time. But the 2, 0 and the 3, 1, they coincide at this 2, 1 point, for example. So they both share an output and an input leg at this time. And so they should, the marginals should coincide on these two things.
Okay.
Is that, sorry, so it's like, so I would, for the 2, 0, I'm just looking at the initial state, the first step and the second step as I've defined them. For the epsilon 3, 1, I'm considering this initial state. I'm taking my O1 to be my initial state. So I'm taking a different initial state for this marginal. And then I'm taking 2, 1 and 3, 2 to be the next steps of that process tensor. And so these are describing two different parts of the stochastic process, and they overlap at one single step.
Right.
So maybe a circuit diagram or something like that would help here. So the 3, 1 might have a possibly different history to the 2, 0. So it might have had a different initial operation, but the kind of the Markov order assumption here is that that's not important, or it doesn't update these statistics in any kind of a meaningful way.
But I mean the whole process, no, the whole process tensor also depends on the, I mean, it's defined through the initial state, right? I mean, having a different initial state defines a different process, right? Process tensor.
That's correct, but the kind of the assumption here is that
I mean, what I mean is like that the epsilon 3, 1, right? I mean, depending on what the state was at 1, which you don't know really, because I mean, it can be a different object, right?
I see. So it's a good question. So there are two kind of components to this. One is what the state actually was. So this matters even in a Markovian sense. So if I'm propagating the state along, then I need to start from the same initial state. So this is taken care of by tracing over that alternate history at this point in time, and then feeding in the new state, which came from the true initial state, if that makes sense. So the purpose, the way that this stitching method works is that the epsilon 3, 1 says the Markov order assumption is that this will not update for any choice of A0. It doesn't depend on the choice of A0 because the correlations aren't too strong. So we apply our A1, and then the future dynamics is cognizant of that A1 because it's made that projection. But the state that you get out at the next point in time is then thrown away. And so only the future is allowed to update. Then you get the state which came out of epsilon 2, 0, which had the real true initial state with the initial operation A0, and that's fed into the next leg of the process. So that the next step, this E32, that has been updated by A1, but it's fed in a different state. Does that?
Yeah, kind of. I mean, it's a bit hard for me to wrap my hand around it because just because of the the output 1, right?
Yep.
That enters the I mean the first leg of upsilon 3 1. I mean, if you don't measure it, how can you feed it like as the initial state to define the upsilon 3 1?
It's like it's a causality issue somehow, right? I mean, it seems so. Yeah.
Because I mean, the process itself, upsilon 3 1, depends on that output, right? It's defined through it.
Which output? Sorry.
Sorry, the output of 1, right? So I mean the upsilon 3 1, it's like the process tensor that kind of is defined through the initial condition, which is the state at time 1, right?
Yes.
If you don't know it because you haven't measured it,
yep,
how can you define the process? Like, I mean, depending on what state you have, you're gonna have like a plethora of possible, as you said at the beginning, right? Like a sort of like all possible.
Right. So in the case where I'm only running unitary operations, I won't know exactly what this state is. That's true. But yeah, so I won't know what the state is because I haven't made any measurements at this point in time. I've only applied unitary operations, but we've still made the characterization for a full span of unitaries. And so you can think of this like what's really happening here is that a unitary operation is really teleporting the state along. So it's propagating that state along, and we're not learning anything about it. But it's still valid to characterize the dynamics. If you have a full span of unitaries, then you can still know how each unitary kind of propagates that state along.
Okay, so
maybe I'm misunderstanding the question.
No, I mean, maybe it's just me that like I'm probably I will definitely read your papers to understand better.
I mean, feel free to send me an email or anything like that.
Yeah, I will do. This is all very interesting. I just so basically just to understand, like if I get it right, like the initial kind of like the process tensor at 1, like this upsilon 3 1, the initial state rho 1 is essentially the kind of like the unitary evolved state rho 0 at time t1 in a sense. And
yeah, and
it
it accounts for any possible initial correlations between the system and its environment as well.
Yeah. Okay. I think I understand. Thanks.
Cool, thanks. So we can see, just to put this into practice, we can see how this works on a real quantum device. So here we have the output results of looking at a 4-step process and modeling it with Markov orders 1, 2, and 3, and then varying the wait time, so varying the interaction time between different steps. And we can see that for short periods of time, all the models do pretty well at reconstructing the dynamics. But as the interaction time or as the wait time is allowed to extend in duration, the models all break down, and we have this kind of delineation between Markov order 1, Markov order 2, and Markov order 3, which shows that there are higher order correlations on these IBM quantum devices. And this is a way to kind of distinguish between them. So I just want to pause there. I have like 5 slides left. I don't know if you want me to kind of briefly go through them or
show them. I mean, maybe briefly go through them, that we have a bit of more time for more discussions, but I mean, we are having lots of discussions already, but yeah, briefly go through them and that we see where this is going. It's an educated audience.
Okay, great. I'll try and go through them a bit quicker. But so as I kind of alluded to before, what's useful about this type of characterization in an extrinsic sense is that it gives you a sense of how to optimally control your system, even in the presence of these sorts of non-Markovian correlations. So here we have, for example, like a 5-step process, and we can consider running a sequence of random unitaries on the device. And so we've characterized this 5-step process, and we're running 5 random unitaries, like 100 sets of 5 random unitaries, and then measuring the state that it produces at the end, and just saying how close is that state compared to the ideal. And so this is not reconstruction fidelity anymore. This is a measure of how good the device is. We then go away and use this process tensor reconstruction and ask the question, if we create the state in the first instance, and then we optimize for what fixed sequence of operations simultaneously increases the fidelity of all of these 100 sequences of unitaries, then we can numerically find that and experimentally apply it on the device. So here's a couple of different dynamical setups where on the x-axis, we have the machine fidelity. So each of these is the ability of the machine to create the ideal state. And on the y-axis is when we recompile it using the characterization. And so you can see not only do we go from about 0.82 to 0.93 on average, or 0.75 to 0.92 on average, but there's a clear separation between the different Markov order characterizations, showing that you essentially get more bang for your buck if you account for higher orders of correlations in order to kind of circumvent them when you want to apply this sort of noise aware recompilation. So this sort of shows that if you do have temporally correlated noise on the device, it can be in a sense engineered away with this sort of a suppression technique like this. But you might also like to know exactly what your correlated noise looks like. So correlated noise is particularly pernicious in a quantum algorithm, particularly because it can kind of propagate through different locations on different qubits.
But now you mean correlations in time primarily, right?
Correlated in time and correlated in space. So in general, an error can propagate through this sort of light cone where it's both information is exchanged with the environment and itself, and also information can go from a qubit to the environment to a different qubit. And so that's what a spatiotemporal error will look like. And these sorts of effects, these are problematic not just because they introduce more error, but because and I'm not an expert at this, but because they can reduce the thresholds of certain quantum error correcting codes, and typically error correcting codes like errors to be kind of independent and identically distributed from one another. So we developed a way to kind of probe these. So firstly, the details aren't too important, but if you use an ancilla qubit, the way that we have in the diagram up here, we can interact our system with that ancilla and then projectively measure the ancilla. And this affects a weak measurement on the system, which we can locally manipulate, and then a post-measurement state. So these are we've designed our own quantum instruments here for this purpose. And we can use this to look at the correlated noise, and in conjunction here, we have the method of classical shadows to look at the two map correlations that exist in these devices. So this left panel shows like a heat map of the total correlation. So this is like a trace distance measure of non-Markovianity between each step in a 7-step process. And in the upper triangular, we have the negativity between these two, sort of showing the different amounts of entanglement that kind of persist. And then these right two panels, these are joint probabilities of different errors occurring at different times. So for example, a probability of a Z error occurring in one time, as well as a Z error occurring in another time, or XX or XZ and ZX. And so this sort of information can feed forward into things like error decoders, but also you could use them as like a more sophisticated estimate for probabilistic error cancellation. Now I want to return, I guess, to the issue of looking at these joint probability distributions, because you might consider that a good use of a quantum computer is to simulate open quantum dynamics and to actually access these quantum features. And in fact, what we recently showed is that processes, quantum stochastic processes, can be every bit as complex as quantum states. So showing that these dynamical sampling problems are equal to some BQP, and that this might be a good avenue to exploring quantum advantage, is to kind of extract the quantum features of these open quantum systems. And so as kind of a direction towards that, we looked at reconstructing much larger processes and getting predicting these joint statistics and characterizing them. So here we have like a 4-qubit spin chain, just like a simple Heisenberg model across 20 steps or 21 times. And we have our same ancilla qubit, which is able to probe this. And we reconstruct the matrix product operator representation of this process, which allows us to characterize the whole thing. And we can also ask the question of what random sequences of instruments, what output statistics these are going to produce, and can we adequately capture these output statistics. So you can think of this like we choose a different instrument, and condition on the instruments, we have a series of joint probability distributions, and I'm obviously not going to go up to 2 to the 21 as my joint probability distribution, but we can look at the different time marginals and our ability to kind of reconstruct or predict these different sequences of mid-second measurements, and find that we can do this up to again about a 99% kind of fidelity. And we can also look at properties of the process as it evolves in time, as well as aspects of the non-Markovianity of the different marginals as they also kind of evolve with time. And as you might expect, it sort of dissipates out on a particularly large process. But this sort of shows, demonstrates how you can take these open quantum system sampling problems and how you can model them, and then hopefully one day how you could take these features and find some meaningful quantum advantage from being able to simulate these open quantum systems, for example, in like a spin boson model setting or something like that. Now, not to kind of overload things, but just to return to this idea of classical shadows as applied to something like a quantum stochastic process. So a question that you might ask, or often I get asked, is how do you know whether non-Markovianity comes from an interaction with a nearby qubit or from an inaccessible bath? And the way that you can kind of answer this question is by doing some causal testing. So if you can apply a causal break to some nearby qubits, then you can essentially, that stops the correlations from persisting forward. And if you still have a non-Markovian interaction, then it can't have come from that qubit who you causally broke. Now, we extended classical shadows to the kind of spatiotemporal regime. And what's interesting about this is that the free observables, so the identity observables that you get non-extensively or logarithmically extensively with classical shadows, in the Choi picture, these constitute a maximally depolarizing channel. So because it's a maximally depolarizing channel, this is a perfectly good causal break. And so you might consider that, for example, down here, if you have a lattice of qubits and some inaccessible defect, here everything's kind of just like self-interacting, and you compute the non-Markovianity, you characterize the non-Markovianity on these, you'll find that they're all non-zero and it's not a particularly useful measure. But if you characterize all of the individual marginals at the same time, you can knock out, or you can essentially erase the different causal pathways that go through other qubits. And what this reveals is that, these 4 qubits here are the ones that are coupled to some inaccessible environment. So this kind of makes the distinction that you might like to care whether correlations are generated by a controllable system or an uncontrollable one. And indeed, you can also generalize this to look for aspects of shared baths. So qubits which are coupled to the same bath, you can simultaneously determine all of these space-time correlations, and that will tell you, that say qubit 2,2 and qubit 2,1 are coupled to the same inaccessible bath. Now, I don't want to go into too much detail here, but just to kind of finish, we've looked into the nitty-gritty, I guess, the process tensor tomography to hopefully kind of convey an understanding of what's going on. Nominally, it seems to suffer from a lot of issues of being expensive and relying on known controls. But we've actually done a lot of work to make it a lot cheaper and a lot more efficient for sparse settings, and to also incorporate a more universal noise framework that estimates both the control operations as well as the environment, as well as interplay of control and environment. And so we've kind of taken this to its sort of logical conclusion, where we estimate these tensor network representations of processes. And this makes things much more efficient, and we can consider larger systems. So for example, we can look at arbitrarily long stochastic processes as long as the correlations aren't too significant. We can look at these space-time correlations, consider like a 2D tensor network of a line of qubits over a series of times. We can also learn the control processes, so we can incorporate these in our models to allow for the fact that the gates themselves might be erroneous, or they might be correlated themselves in time. And we can also do things like use ancilla qubits as probes of a system and learn exactly what these testers look like simultaneously, so that you can get a full picture of the stochastic process without actually having access to mid-circuit measurements. So thanks for sticking with me, and thanks for a great discussion. A couple of areas in which I think would constitute interesting research areas is firstly looking at what sorts of processes give rise to interesting temporal correlations. So, what kind of open quantum systems can you set up to have an interesting class of exotic quantum process? The second is what I already kind of talked about, which is that, obviously a lot of work has been done recently to extract properties of quantum states and feed them into, say, machine learning algorithms and find speed ups in that regard. It seems as though the exact same thing should follow for looking at a single qubit and sampling that across many times. Although there are some bottlenecks to that approach. I think there are avenues for applying this in a quantum sensing setting. So like if you have a nitrogen vacancy center in Diamond, and that's coupled to some environment that you want to learn, that this can kind of tell you significantly more information than you might otherwise learn from those things. I think it's a really important problem to look at taming correlated noise, both from an error suppression context, but also error mitigation and error correction context, for which you need these kind of tomographic tools. And I also think it would be a really interesting problem to study like a renormalization group flow of processes. So look at fine graining and coarse graining and determining kind of emergent temporal features of these processes. And I actually think that this could be a really interesting direction for the modeling of emergent errors in possibly much larger quantum computers. Finally, I'm looking at putting together a software package, although I keep delaying this particular step. But hopefully at some point we'll be releasing a software package for the community to use. So thanks very much for listening. I appreciate all the discussion and I appreciate your attention. And if there's any final questions, let me know.
Wonderful. Thanks for the enjoyable ride through these quantum stochastic processes. That was really wonderful. And as you can see from the many questions, that really hit a nerve in many ways. Yeah, we had lots of questions along the way. We may have a couple of extra questions and then keep the further discussions like maybe separate.
Yeah, absolutely.
In the future. I mean, I have, of course, loads of questions. I will have to kind of constrain myself. Maybe I ask other people to ask first. Is there any further question? Giacomo, you had your question that you swallowed a bit.
Yes. I mean, I have asked already tons of them, but I mean, this has been probably the most exciting talk I've heard of in a while. So thanks for that. So no, basically, I have a sort of like another like clarificatory question in a sense. I mean, just to understand if I got it right. So I mean, you are kind of like accessing the properties, basically temporal properties, multi-time properties of your process by essentially, I mean, using this process tensor kind of formalism, being able to look at the final output like as a finite time, right? So I was actually wondering, I mean, can you also, I mean, and you always calculate, for example, the trace, or the fidelity or the trace distance, or like some measure like that of whatever basically data you have with the simulated version, right? Can you also I don't know, like look at something like, I mean, multi-time correlation functions. I mean, can you reconstruct them as well using this properties, or? I
Yeah,
guess,
absolutely.
Right?
Yeah. So I should emphasize that a process tensor, it makes it sound like you don't look at the state until the very end of the circuit. You only get this kind of final time state. But it satisfies this containment property that each shorter process tensor is contained in the larger process tensor. So if I have a 4-step process tensor, I also have the 3-step, the 2-step, and the 1-step process tensors. And so I can access my states at those points.
Mm-hmm.
You can look from this information, you can compute any multi-time correlation functions that you like. So what I flashed up, these were measures of non-Markovianity. So principally what we use is if you compute the quantum mutual information between your process tensor and the tensor product of its marginals, then this can be shown to be a measure of non-Markovianity, or in a precise way. You can also compute any kind of correlation functions that you're interested in. If those are non-zero, then that will also be a signature of non-Markovianity. But it gets a little bit subtle in terms of the types of correlation functions that you're interested in and how that reflects the dynamics. So
right.
Say if you looked at correlation functions between the different output legs. So, saying I have a measurement at output 0, a measurement at output 1, and a measurement at output 2, and I'm looking at the multi-time correlations there. That will only be non-zero if you have non-unital dynamics. So if you have dynamics which is unmixing the state and then allowing it to kind of regain some coherence. Whereas if you look at multi-time correlation functions, which include input legs, and you can kind of circumvent that. So the going off on a tangent, but there's some subtlety to it. But the exact same way that you can compute correlation functions of quantum state, you can also do it of a process. You just need to kind of incorporate some of the context of that process into it.
And I have also another like curiosity on slide 18. If you can go to.
Yeah.
Yeah. What are those basically linear lines, that the dashed lines in the plots? I mean, why the machine fidelity basically linearly grows in time? Linearly grows. I mean, what is that like?
Oh, the dashed line is just a y equals x. So you can see that anything above this line is a better result than
Okay.
They would have produced. So yeah. So no, this is just that's just for the sake of being able to read the graph.
That's cool.
Maybe a short question on my side.
Thanks a lot.
You mentioned that this a couple of times, like twice, this kind of sampling method. So what you mean is like you want to look at the kind of the hardness of sampling, but now including a temporal aspect, where you say that sampling from a kind of process, including a temporal component, is kind of hard in a precise sense, that you can't efficiently classically simulate from a nearby distribution classically efficiently, right? Can you make this more precise, what the presumed and hoped statement could be?
So the presumed statement of advantage or of complexity?
No, both. I mean, is that a conjecture, or have you proven this, or what's the status of this?
So we've shown that that this particular complexity class. So this is in this reference, the second last reference. Where we consider a complexity class of dynamic sampling problems which are generated by polynomially sized interactions with an environment, we've proven that this complexity class is equal to some BQP. And there are actually some really instructive examples of this. You can construct some really contrived examples of this. I don't know if you're familiar with the 1-qubit trick for Shor's algorithm, where you condense the whole register in which you do a quantum Fourier transform into a series of sequential measurements, and then feed forwards of those measurements. And that sampling problem across time that allows you to factor the number. And so this is actually like an example of like a dynamic sampling problem on an open quantum system, which I mean, it's a very contrived one, but it allows you to factor numbers.
Wonderful. No, I even get kind of elements of the reduction, the way you put it. Wonderful. That's great. So now it's 11:30. There's loads of more stuff to ask. But let's maybe do this in a smaller round very soon. I sent you a link. That was really great. That was fascinating. And thanks for the many questions along the way. That was really great. Thanks for the inspiring talk.
Thanks so much. Thanks for engaging.
That was really nice.
I really enjoyed this.
Yeah, me too. That was great. So yes, thanks to all for coming. Thanks for the wonderful talk, and talk more to you soon.